Welcome back. So we've looked at a lot of ways that we can generate polynomials from zeros that we know, but the big question is how do we get those zeros in the first place? What are some ways that we can do that? Now we saw that factoring is a way and things like that, but factoring is pretty limited, especially when those polynomials get really large. So what are some other techniques? Well, this next one is a really awesome way to get a list, at least a potential list of zeros. It's not necessarily going to give you the zeros, but it gives you a list of what they could possibly be. And it's called the rational zero test. So if we have some polynomial of degree n, so you can see we have to the nth power here, and it has integer coefficients. So again, everything should be real in your polynomial here. Then every rational zero of f has the form of this. Rational zero is equal to p over q. Well, what's p and q? P and q have no common factors other than 1, and p is equal to a factor of the constant term, a sub 0, and q is a factor of the leading coefficient, a sub n. So really all of this business in the middle we don't care about when we're looking for possible rational zeros. All we care about is the leading coefficient and our constant term, a sub 0. So that's a really nice rule that we can use to help narrow down the possibility, that usually infinite possibility of zeros that you might have. So let's take a look and see what we can generate. Now this question just wants a list, so be careful about the wording on these. If it says list, that's all you need to do is make a list. You don't need to check or anything. So it says list all the possible rational zeros of the function, f of x equals blah, 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 blah. So first things first, let's make sure we get our p's and q's correct. So if we had our p's, so remember p is a factor of the constant term, a sub 0. So our constant in this case is 45, or negative 45, depending on how you want to look at it. So the way we take care of the pluses and minuses is exactly that. We'll just put a plus or minus in front of all those possible factors. So for 45, we know that 1 goes into that. 1 goes into everything. So plus or minus 1 is one or two of those factors. The next factor of 45, well, 2 doesn't go in, 3 does. So we'd say plus or minus 3. How about plus or minus 5, plus or minus 9, plus or minus 15, all the way to plus or minus 45. I don't believe there's any other factors that will divide evenly into 45. So there's our potential p's. Our q's should be factors of the leading coefficient. Well, the leading coefficient in this case is the 2. So what are the factors of 2? Well, there's not a lot. Plus or minus 1, plus or minus 2. And that's it. All right, so now that we have our p's and q's, now we have to put them into our fraction form here. So our rational zeros are always going to be p over q. So let's see what that looks like. P over q. Well, let's go down the list of p's and put it over each possibility of q. So let's first start by putting all of those over plus or minus 1. But plus or minus 1 doesn't really change anything. So really, the first list is all of p. Now, we're not going to get too crazy about putting them in numerical order or anything like that, because you can see once we start using q of plus or minus 2, then we're going to start getting fractions in there. And some of those fractions obviously will fit chronologically into our list in different spots, but we're not going to get too crazy. So let's just put each of our p's over our q of plus or minus 2. So that's going to give us a plus or minus 1/2, plus or minus 3 halves, plus or minus 5 halves, plus or minus 9 halves, 15 halves, and 45 halves. Now, sometimes there will be some overlap as a result of putting all of these different combinations of factors together. So if we had gotten, 6 halves or something like that, 6 halves is 3, which we already have over here, so we don't need to write it twice. So again, just make sure there's no redundancies and leave those out. But in this case, there are no redundancies, so this would be the entire list of possible rational zeros. Now, that's a lot. That's a lot of possibilities, but we're going to see later on how we can reduce our list down a little bit as well. But for now, at least we have a starting point. So God forbid you don't have a calculator or a graphing calculator and you can't graph it. This is what they used to do back in the old days. They would at least get this possible list, and then they could check to see which ones are zeros and which ones weren't pretty quickly, if any. So, all right, let's apply this to a couple of problems. So this first one says to actually find all of the real and imaginary zeros for each polynomial function. So we got f of x is equal to x cubed minus 9x squared plus 26x minus 24. All right, well, again, we could try to factor this. We've done factoring by grouping and things like that, but I have a pretty sneaking suspicion that this is not going to be able to be solved using factoring by grouping. So let's use our new trick and get a list. So remember, P is going to be factors of the constant. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. So again, all of these numbers divide evenly into 24. That's all we're looking for. But since our Q is equal to 1, plus or minus 1 to be technical, then P over Q is the same as P. So I'm not going to rewrite it. So we know what our possible rational zeros are. So now what should we do from here? Well, we're going to need to see if we can find a zero. So we have to just start trying some of these and see if we get lucky and find one that gives us a remainder of 0. So remember, we can use that remainder theorem, factor theorem, to determine if we have a 0 or not. A lot faster than just plugging it in and seeing if we get 0 as a result. That is a little bit more time consuming because of all those exponents. So let's start in the middle. Let's start at 4. So if I said 4, and I wanted to see if it divided in with a remainder of 0. So we got to make sure we do our synthetic division carefully and correctly. So 1, 4, negative 5, negative 20, 6, 24, and I am either really lucky or I remembered from back in my brain of what possible zeros this had. But like I said, we got lucky and found a 0 right off the bat. But we could have tried any of these other ones. I mean, we could have tried 3, to see what we get as well. We could have tried 6. I grabbed 4 just randomly, but let's just try 6. So 1, 6, negative 3, negative 18, 8, 48, 24. So that one was not a 0. But like I said, once you find 1, in this case, we can stop. We don't need to keep going and checking for other ones because this is a third degree polynomial. So if we found 1, that means there's only 2 more that are left. So we can actually use this and rewrite our polynomial. So we can say that this is x minus 4 because we have k is equal to 4, and then times what's left. And remember, this tells us what's left. So we got x squared minus 5x plus 6. And again, we're just setting this equal to 0 because we're trying to find those zeros. So now, since it's quadratic, we have all kinds of methods to break this down. But factoring will work on that. So we want factors of 6 that add to be 5. And because the sign is positive, we know they're the same. And because this sign is negative, we know they're both minuses. So factors of 6 that add to 5. Well, I think you know it's got to be 2 and 3. So this is the factorization for it. But again, answer the question. The question wants the zeros, doesn't want the factorization. So go that last step and say, okay, well, x has to be 4, x has to be 2, and x has to be 3. So we could have actually, we got lucky and found 4 first, but if we had picked 2 or 3, one of those would have worked as well, and we would have been able to do the same kind of method to break this down. All right. So let's try one more. And I think actually I will hold off on doing this one into the next video. So, psych. See you in the next one.